Okay, welcome back everybody. So now we're looking at conditional probability and independence. Now we did speak briefly about conditional probability last time, you might remember. Today we're going to focus on the formula that we can be used for this. This is something that's really important because quite often all of the areas of probability we're going to cover down the track, quite often we need to use this conditional probability formula in conjunction with some of the other probability distributions we will learn later on. So when we're looking at conditional probability, a few important things to start with. This is when we're seeing particular phrases like given that. So for example, if we want to know what is the probability that I roll a 6 on a die, given that the number I roll is greater than 4. So it's giving a certain condition about our answers. We can have the phrase given that. Other phrases are sometimes knowing that. So we could ask, what is the probability that that a fish found at random from the ocean is 142 centimeters in size, knowing that it is longer than 160 centimeters. Another phrase that we can use is just if. So calculate the probability that we roll a 6 on a die if the number shown is greater than 3. Alright, so our actual probability here, probability A, this straight vertical line, it needs to be directly vertical. We read it as given that. So we're wanting to calculate the probability that A occurs given that B occurs. In the top here, remember this is the intersection. We defined this before. So this probability A intersect B. That means we want to know for what values, which elements of the sample space both A and B are true. Now we can rework this conditional probability formula to give us the multiplication rule. So all we've done is that we've taken our conditional probability formula that we had here, and if we multiply both sides by a probability of B, we end up then with another rule that we can see down here, which is our multiplication rule. Okay, and this comes into play a little bit later on. One thing to remember is that this conditional probability formula, it is not on the formula sheet, but it is very, very important in probability. We're going to need to use it a lot. So this is something that you will need to learn by heart. The other thing we're talking about today are independent events. So these are events where what happens with one has absolutely no impact on another, no effect on another. So there's a few different examples we could think of for this. One might be if we're throwing a dice and a coin. So if we're rolling a dice and flipping a coin, what happens with one doesn't impact the other. If we got a 6 on a die, that doesn't in any way impact what will happen when I flip the coin. So those are our independent events. If we're thinking about events that might not be independent, if we were looking at the probability of it raining on a day and there being a car crash, I would say those probably are not independent because the rain would have some impact on how many car crashes there are and how safely people drive. Independent events are when we have no effect, okay? We've got our formula here for independent events. So what we're saying here is the probability of A given B is equal to the probability of A. So what we're saying there is because they're independent, what happens here with this probability of B? It has no effect. It's the same as just considering the probability of A. The other converse or opposite of this would be the probability of B given A. In this case we're saying what happens with A, it has no effect on B, so it's the same as just working out the probability of B. When we have two independent events, when probability of A and B are independent, to find the intersection, remember that's what this little N looking symbol looks like, all we do is we multiply the probabilities of each of those things happening. So to use this formula, we have to first know that the two events are independent, and then therefore we can use this particular rule. Our last definition, I think, for today are mutually exclusive events. So mutually exclusive events, I think I did mention these in our last clip as well. If we think about showing this as a Venn diagram, if I've got mutually exclusive events, it means that there is no intersection, okay? So this means that if I'm trying to find probability of A intersect B, I'm going to get 0, because this means that they cannot happen at the same time. So A and B cannot occur together. If one of them occurs, we can't have the other occurring. An example here might be if you roll a dice, it can't be a 6 and a 5 at the same time. If you roll a dice just once, the number you see, it has to be a 6 or a 5. It can't be a 6 and a 5, so therefore they are mutually exclusive. If we can't use the word and about two events, then they are mutually exclusive. Another example is that you can't, if you are to perform in a race, you can't win a race and lose a race. It's one or the other. They are mutually exclusive. If events are independent, then they are not mutually exclusive, because the whole point of our independent events is that they have no effect on each other. Or another way of thinking about independent events is that they are unrelated. So if we have unrelated events, then they are independent, and therefore they're not going to be mutually exclusive. So let's have a look at some examples together. Okay, in our first example here, we have got a particular situation here where we've been given boxes of chocolates. Kelly's box contains 5 solid milk chocolates and 3 with caramel centres, and Tanya's box has 4 milk chocolates and 4 with caramel centres. Now to start with, we're going to construct a tree diagram. When we're doing a tree diagram, we have to think about what thing comes first. What are we determining first? Is the first thing going to be which type of chocolate we choose? Or is the first going to be which box we choose? Hopefully you've had a think about that. If we're wanting to choose a chocolate, the first thing we're going to do is determine which box we're going into. So the first thing we're going to do, and I may run out of room here, we'll see how we go. The first thing we're going to do is either we're going to choose from Kelly's box or we're going to choose from Tanya's box. You might remember we drew tree diagrams in the last video as well. This time, the probability of Kelly's box and Tanya's box, are these equally likely? Yes, it tells us there is an equal chance of selecting each box. So that means I've got half a chance of selecting Kelly's box and half a chance of selecting Tanya's box. And we write the probabilities on the branches. Once we've chosen Kelly's box, then I put my hand in to choose a chocolate, and it could be a milk centre or it could be a caramel. If I put my hand in Tanya's box, I could get a milk chocolate or I could get a caramel. It tells us down the track that we're talking about a chocolate selected at random, so therefore we assume that there is an equally likely chance of choosing any of those chocolates. Kelly's box has 5 solid milk chocolates, 3 with caramel centres, so the chance of getting a milk chocolate will be 5 out of there are 8 chocolates in the box, or a caramel, there are 3 out of 8 there. Tanya's box has 4 solid milk chocolates, so it's 4 out of 8, or of course we could simplify that to a half. And there is 4 out of 8 chance of getting a caramel, which we can simplify to a half. Because all of the branches here are not equally likely, we need to put the probabilities written on the branches in this case. It does not matter if the probabilities are written as fractions or as decimals, that's entirely up to you. Alright, so that was our answer to part A. Now we get on to part B. Calculate the probability, so we want PR, remember our notation, in brackets, we write the event in the brackets, that a chocolate selected at random is a solid chocolate from Callie's box. So we're wanting Callie's box and a solid chocolate, which I was using before, solid milk chocolate here, I was using an M for that. So if we're wanting this, we're wanting Callie's and milk, we're wanting to follow this pathway to this part of the sample space. If we think about this happening, we're wanting a chocolate that is going to be, it's going to be from Callie's box, and it's going to be one of the solid milk chocolates. When we say the word and, I want you to think whenever we see this that we think independent events, okay? When we're saying and, we're getting independent events. And when we're saying and, we multiply. So Callie's and milk chocolate, that means we're going to do half times 5 on 8, which we can multiply to give us 5 on 16. Another way to think about this is when I go along the branches, when I follow along branches like this of a tree diagram, I multiply every time I move along branches because I want both of these things to occur. They're independent events. Our last option C, our last question, calculate the probability, PR, that a chocolate selected, oops, we don't need the and there, that a chocolate selected came from Tanya's box. So Tanya's box, given, so here's this conditional probability, given, I need my straight vertical line, it has a caramel center. Now when we're setting this up, our first part is always what it is that we're wanting to find the probability of. This T is what we're trying to find the probability of, and it wants us to calculate the probability that a chocolate selected came from Tanya's box. Given, this is our given sign here, that it has a caramel center. The order we set this up is very important because it will influence the equation that we're about to set up. So our formula says that we then have probability of Tanya's intersect caramel divided by the probability of a caramel. So the probability of Tanya and caramel, we follow our branches, Tanya and caramel, we're getting to this sample space here, the TM, and the independent events, we multiply, it's half, we're multiplying, so we're going along the branches, half times half, divided by probability caramel. So for this probability caramel that we're looking at here, we've got a few different things to follow. Our caramel means we want this option here, it could be Callie's and caramel, or this option here, we could have Tanya's then caramel. Notice I said we can have this or this option here. When we say or in probability, it indicates plus. When we say and, as I mentioned before, it indicates times. So if we're following along our branches here, we can have Callie and caramel. Half and means times, 3 over 8. So we can have Callie and caramel, or means we come back to the start here, or means we say plus. We can have Tanya and caramel. So that's going to be half times half. Now we need to simplify this, and sometimes this question, this type of question, can be found in the tech free, which means you do need to know how to work with fractions appropriately. In our numerator, half times half, that's going to give me 1 over 4. And I'm going to say this is divided by, remember fractions mean divided by. In our denominator, half times 3 over 8 gives me 3 over 16, plus half times half gives me 1 over 4. So if we're trying to work this out, we've got a quarter divided by, well, we need a common denominator to add our fractions, so I need to make my second fraction out of 16 as well. A quarter is the same as 4 out of 16. I can add these together to give me 7 out of 16. And finally, again coming back to your fraction knowledge, remember when we divide by 7 over 16, it's the same as multiplying by 16 over 7. I can cancel divide by 4 in both, so the probability is 4 over 7, and this is our final answer. A good check is to remember that our probabilities should always be between 0 and 1, which this one is. Let's do one final example. Okay, so we want to find the probability that in 3 tosses of a fair coin there are exactly 2 tails, given there is at least 1 tail. First thing when we're doing stuff like this is that drawing a tree diagram is really useful. Okay, please do use tree diagrams. They're a great way to understand what's going on with probability, particularly when we have independent events, which these are, because throwing a coin 3 times, that is independent. What happens on the first toss doesn't have any influence on the second or the third. So we can get heads, then tails. In our second toss we can have heads, then tails, and then our third toss we again have the choices of heads, then tails. Notice with our tree diagram we're writing the outcomes at the end. Now with this one we know that this is a fair coin, so when we think of what a fair coin means, another way that we could say that is that it's unbiased, or that all options are equally likely. When we have all options being equally likely, you can, if you like, list all of them as having a chance of half on our branches, but remember, as from earlier, when all options are equally likely, that means that all options in the sample space are also equally likely. So if we don't want to work it out in the traditional way, we can do it this way as well. It's up to you which way you would prefer to work with this one. So I'll indicate both of them and you can make a decision. So here is our sample space. I've followed along each of the branches and we've got 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Okay, we need to find the probability that there are exactly 2 tails. That comes first, that's what we're finding, given that there is at least 1 tail. So that means given that we're getting greater than or equal to 1. Our formula, probability 2, and probably a good way to set this up actually, now that I think about it more, because it's not really good notation to write this like this. If we start by defining a variable, which is something we'll come up to later, if we let x equal the number of tails, because that's what we're interested to, a better way to set this out with better notation is to say we want x to equal exactly 2 given x, our number of tails, is greater than or equal to 1. So we will get probability x equals 2 intersect with x greater than or equal to 1 divided by probability x is greater than or equal to 1. If we think about where this happens, our values here, our options for our tails, is we could get 0, we could get 1, we could get 2, or we could get 3 tails. These are our options. For x equal to 2, we want just this possibility. For x greater than or equal to 1, it could be this option, 1, 2, or 3. The only place they intersect, these both occur, is just here. So this is actually the same as saying the probability x equals 2 over the probability x is greater than or equal to 1. Probability x equals to 2, we have, if we want to get 2 heads, now we've got to think about how many ways this can happen. To get 2 heads, we've got this option here. Oh, sorry, not 2 heads, 2 tails we want. I take that back. 2 tails, we've got this option here, or we've got this option here, or we have this option here. So altogether there are 3 out of 8 chances divided by probability x is greater than or equal to 1. So greater than or equal to 1, we'd be looking at 1 or more tails. So that means we've got this option, 1, 2, 3, 4, 5, 6, 7 options. 7 out of 8. So we can work this out. This is going to be 3 out of 8 divided by 7 out of 8. Using our fraction skills, this is the same as times 8 over 7. Cancelling down, we get our final answer of 3 out of 7. And this would have worked the same if we had have used our probabilities on the branches. If I'd needed to work out this 3 out of 8 using the probability branches, it would have taken longer, but it would still have worked. I would have needed to follow our branches along. Half times half times half gives me 1 over 8 for this option here. Plus, because or, the other option is to come back here. Half times half times half. That would give me another 1 over 8. Or our final option, so we add again, we come back to the start. Half times half times half. And if we add our options 1 over 8 plus 1 over 8 plus 1 over 8, we would again get that 3 over 8 option there. So both will work. Okay everyone, that's it for today. I hope to see you again soon.